Find a particular solution to y double prime plus 4y equals cosecant squared of 2. We need the complementary solution yc to construct our substitution. The characteristic equation for y double prime plus 4y equals 0 is k squared plus 4 equals 0, which has roots k equals plus or minus 2i. So the complementary solution, c1 sine of 2t plus c2 cosine. Replacing the arbitrary constants with unknown functions v1 and v2 gives us our substitution. Yp equals v1 sine of 2t plus v2 cosine of 2t, with the condition that v1 prime of sine of 2t plus v2 prime of cosine of 2t must equal 0. Now we need the derivatives. Yp prime will be 2v1 cosine 2t plus v1 prime sine 2t minus 2v2 sine 2t plus v2 prime cosine 2t. Here we can apply the condition that v1 prime sine of 2t plus v2 prime cosine 2t equals 0 to simplify the first derivative before we find the second derivative. So yp prime is just v1 cosine 2 minus 2v2 sine 2t. The good news is that this always happens when finding the first derivative. Now, the second derivative is negative 4v1 sine 2t plus 2v1 prime cosine 2t minus 4v2 cosine 2t minus 2v2 prime sine 2t. Plugging the particular solution and its derivatives into the differential equation gives y double prime plus 4y equals cosecant squared 2t, which thankfully can also always be simplified. Just like in reduction of order, all of the terms with just v1 and v2 should cancel. This leaves 2v1 prime cosine 2t minus 2v2 prime sine 2t equals cosecant squared of 2t. Now we have an equation involving two unknown functions, v1 prime and v2 prime. To solve for two unknowns, we need two equations. Where can we get a second equation involving v1 prime and v2 prime? Our condition v1 prime sine 2t plus v2 prime cosine of 2t equals 0 is the second equation. You can solve the system by any method you want, but I recommend using Cramer's rule. I remember learning this in college and getting super frustrated trying to solve these systems using substitution or elimination. The system we need to solve is 2v1 prime cosine 2t minus 2v2 prime sine 2t equals cosecant squared 2t, and v1 prime sine 2t plus v2 prime cosine 2t equals 0, which we can represent with a matrix equation: 2 cosine 2t, negative 2 sine 2t, sine 2t, cosine 2t, times v1 prime, v2 prime, equals cosecant squared 2t 0. So A is 2 cosine t negative 2 sine t, sine 2t cosine 2t, and B is cosecant squared 2t 0. So A1 is cosecant squared 2t negative 2 sine 2t, 0 cosine 2t, and A2 is 2 cosine 2t cosecant squared 2t sine 2t, 0. The determinant of a is 2 cosine 2t times cosine 2t minus negative 2 sine 2t times sine of 2t, which equals 2 cosine squared 2t plus 2 sine squared 2t, which equals 2. The determinant of a1 is cosecant squared 2t times cosine of 2t minus negative 2 sine 2t times 0, which equals cosecant squared 2t cosine 2t. And the determinant of a2 is 2 cosine 2t times 0 minus cosecant squared 2t sine 2t, which equals negative cosecant 2t. Now using the Cramer's rule formulas, v1 prime will be the determinant of a1 over the determinant of a, so cosecant squared 2t cosine 2t over 2, and v2 prime will be the determinant of a2 over the determinant of a, so negative cosecant 2t over 2. Now we need to integrate to find v1 and v2. v1 is the integral of v1 prime dt, so the integral of 1/2 cosecant squared 2t cosine 2t with respect to t, which equals 1/2 the integral of cosine of 2t over sine squared 2t dt. This integral can be evaluated using substitution. Let u equal sine of 2t, then du equals 2 cosine 2t dt. This integral becomes 1/2 of the integral of 1/2 du over u squared, which equals 1/4 times negative 1 over u, so negative 1/4 1 over sine 2t, or negative 1/4 cosecant 2t. We don't need integration constants here, but it's not wrong to include them, and we'll see why at the end. v2 is the integral of v2 prime with respect to t, so the integral of negative 1/2 cosecant of 2t dt equals negative 1/2 the integral of cosecant 2t dt. This time I'm going to let u equal 2t, du equal 2 dt to rewrite this integral as negative 1/4 integral of cosecant of u du. I'd be surprised if you had this particular antiderivative memorized. Instead, you can just look it up. So v2 is negative 1/4 times the negative natural log of the absolute value of cosecant of u plus cotangent of u, which is positive 1/4 the natural log of the absolute value of cosecant of 2t plus cotangent of 2t. Again, no integration constant needed. Finally, since yp is v1 sine of 2t plus v2 cosine of 2t, yp equals negative 1/4 cosecant of 2t times sine of 2t plus 1/4 natural log absolute value cosecant 2t plus cotangent 2t times cosine of 2t. So yp equals negative 1/4 plus 1/4 cosine 2t natural log absolute value cosecant 2t plus cotangent 2t. Since the problem only asked for a particular solution, we're done. But before I end the video, let's see what would have happened if we had included integration constants when we found v1 and v2. We would have written v1 equals negative 4 cosecant 2t plus c1, and v2 equals 1/4 natural log cosecant 2t plus cotangent 2t plus c2. So when we substituted to find yp, we would have gotten negative 1/4 cosecant 2t plus c1 sine 2t plus 1/4 natural log of absolute value of cosecant 2t plus cotangent 2t plus c2 times the cosine of 2t, which we would then rewrite as yp equals negative 1/4 plus c1 sine 2t plus 1/4 cosine 2t natural log cosecant 2t plus cotangent 2t plus c2 cosine 2t. The new terms that the integration constants give us are c1 sine 2t and c2 cosine 2t, which should look familiar because they are the two halves of the complementary solution. So all that happens when we include integration constants is we get the full general solution instead of just a particular solution. But to use this method, we always have to start by finding the complementary solution. So even when we want the general solution, we can still leave out the integration constants when finding v1 and v2, and then just add the complementary solution at the end.